All of the examples we've looked at so far have had even number of electron pairs, but you don't have to have an even number of electron pairs. So let's talk about an example of a molecule that has an odd number of electrons, and let's look at nitrogen dioxide. Now, if you have an odd number of electrons, it's called paramagnetic, or a free radical is sometimes what it's referred to, and NO2 is a great example of that. So let's build a Lewis structure for NO2. So like before, central atom, usually listed first, lowest electronegativity, etc. It's going to be nitrogen, no question. Now, valence electrons. Nitrogen is 5, and oxygen is 6, and there's 2 of them. So 6 times 2 for the oxygen, 12, plus 5 for nitrogen, 17 valence electrons. So this is definitely a difference now, because if you have 17 valence electrons and you try to divide it by 2, so what I do personally in these kind of situations is if you run into an odd number of electrons, 17 divided by 2 would be 8 pairs plus 1. And this plus 1 just helps me remember that we're going to have one extra electron kind of floating around. And that extra electron has to have its own room. All right, it can't be bonded with any of the other pairs. And I'll show you this here in a little bit. So what we would do is we put nitrogen in the middle, oxygens on the outside. You'd start by drawing a single bond between the oxygens to keep them connected. You'd then give each oxygen a filled octet, i.e. 3 lone pairs around it. But if you do that, you're left with then an oxygen, nitrogen, oxygen, where the oxygens have their octet, but you've got this one electron left over. So what you would do is you'd put the odd electron on the nitrogen, all right? But if you look at this structure now, nitrogen doesn't have even anything close to an octet. It has 2 bonding pairs and a lone pair. And it needs to have at least 4 types of things, of pairs, whatever, around it. So in the final version, which is shown in the lower left right there, one of the lone pairs comes from the oxygen on the left to make a double bond, and that would make the N happy. All right, like this nitrogen right there has a double bond on the left, a single bond on the right, and a lone pair, so 4 pairs around it. But really, there's no reason why you couldn't have taken that lone pair from the right oxygen. So you could also have this structure right here. So this particular molecule is what they call a resonating molecule. And it's another thing we'll talk about a little bit more here in a little bit. But before we go into resonance, paramagnetic things are just a lot more reactive. They're attracted to magnets. They do different things that the other things don't. Most of the materials around us are diamagnetic, and diamagnetic things are not attracted to magnets. So when you have a paramagnetic molecule, you have to be careful, all right? It'll do things that the diamagnetic things won't, and you can draw Lewis structures with them. The important part is just give that lone pair its own space. So if nitrogen can handle 4 things around it, like 4 bonds, that lone electron is going to take up one of those 4 places. You wouldn't try to jam it in with another one. You wouldn't want to make 2 double bonds to the oxygens, because then nitrogen would have 4 bonds and a lone pair. That would be more than the octet. So the lone pair just takes up one of the pieces in the octet. Let's talk a little bit more about resonance, why we did that. So sulfur dioxide is SO2. Let's do a Lewis structure for this. Central atom, sulfur, definitely. Oxygen's on the outside. Sulfur and oxygen have 6 valence, so 6 times 3 essentially is 18. Divide that by 2, 9 pairs. Put the lone pairs around the atom. You can see that oxygens have fold octets, but sulfur with a lone pair and 2 bonding pairs does not have an octet. And sulfur wants to have an octet. The only ones that can go under are boron, beryllium, aluminum, those kind of things. Sulfur is not in that list, so sulfur needs an octet. So we would make a double bond. You could take an electron pair from the left oxygen to make a double bond, but you could also take one from the right to make a double bond. Either way is fine. So the question is here, which way is better? Is it better to take one from the left? Is it better to take one from the right and make a double bond? And this leads into the idea of what's called resonance, because really, energetically, there's no difference taking a lone pair electron from the left to make a double bond or taking a lone pair from the right oxygen to make a double bond. They're energetically similar. So this leads to what we saw with the NO2 example. This leads to resonance, all right? And resonance is when you have more than one possibility for a double bond. Now, in reality, you don't have two separate molecules. You have like 1.5 bonds on the left and 1.5 bonds on the right. So you see a hybrid, a mixture of these two resonance forms. But to make sense of it in our world, people will usually draw both resonance forms, and then the hip chemist will know that the actual version is a mixture of the two. So for the NO2 example then, there would be oxygen on the left with a double bond, and then oxygen on the right with a double bond, and it would hybridize back and forth between them. You'd have a 1.5 bond. When it comes to resonance structures, sometimes there will be a question as to what is the better resonance form. And better here means more stable, okay? And chemists use what's called a formal charge to determine the most stable Lewis resonance form. And these can be actually pretty helpful. Now, formal charges are a little bit weird, but it is a powerful tool in the chemist's arsenal when you're creating a Lewis structure, so it's cool to think about. The definition of formal charge is kind of strange, but what you're going to end up doing is you're going to find a formal charge, which is a type of a charge on each atom in a Lewis structure. The Lewis structure with the most zeros is going to be the winner, all right? It's going to be the best Lewis structure possible. So how do you calculate formal charge? Great question. Formal charge, there's different ways to do it, but what I like most of the time is I use the fact that the formal charge on each atom is going to equal the group number of the atom minus the number of bonds minus the number of lone pair electrons. And so you'll calculate this formal charge on each atom in the Lewis structure, and you want to have the most zeros possible. Now, if you've done everything right, when you add up all of the formal charges in your molecule, the sum of the formal charges must equal the ionic charge. And I'm sure at this point, this is like kind of gobbledygook to you. So let's look at some examples and figure out how you would use formal charges to tell what the best structure is.
Formal charge calculations can often help us identify the most stable isomers of molecules. Consider the isomeric compounds, hydrogen cyanide and hydrogen isocyanide. Both structures have octets of electrons about carbon and nitrogen. The formal charge on carbon in hydrogen cyanide is 0. Similarly, the formal charge on nitrogen is 0. In hydrogen isocyanide, the formal charge on carbon is -1. The formal charge on nitrogen is +1. Because the formal charges are non-zero in hydrogen isocyanide, we can predict that this isomeric form is less stable than hydrogen cyanide, as found to be the case.
So this is an example of how you can use formal charges to tell what is the more stable structure. And on the right-hand side there, we have hydrogen cyanide in the top, which is an H followed by C and then N. And in the lower part there, that's hydrogen isocyanide. It's a hydrogen with a nitrogen in the middle followed by carbon. Now, if you followed electronegativity rules, carbon would go in the middle because carbon's the lowest electronegativity. Nitrogen would be on the outside, the higher electronegativity. But you can actually make the isocyanide compound where the nitrogen's in the middle and carbon is on the outside. So let's see if electronegativity helps us out here by predicting a stable molecule or not. And so what you would do is you draw the Lewis structure and then calculate the formal charge. So for hydrogen, which is pretty easy, hydrogen has a group number of 1. That's the 1A on the periodic table. It has one bond, the hydrogen-carbon bond. So we'd have group number 1 minus 1 bond. Hydrogen has no lone pair electrons. So 1 minus 1 minus 0, that's where the zeros come from. So both of these hydrogens have a formal charge of 0. No big deal. If you go to the carbon in the hydrogen cyanide, that carbon is a group number 4. It's 4A on the periodic table, so 4. 4, and that carbon has 4 bonds, 1, 2, 3, 4 sigma bonds, no lone pair electrons. So it would be 4 minus 0, formal charge of 0. Cool. Now the nitrogen on the end of hydrogen cyanide, group number 5, it has 3 bonds to carbon, so 5 minus 3, and this has 2 lone pairs. And notice that you count each lone pair electron in this calculation. It's not the lone pairs total, it's lone pair electrons. So you'd go 5 minus 3 bonds minus 2 lone pairs, formal charge of 0. Now if this is a good Lewis structure, and it's a good thing, all the formal charges together should equal the charge on the molecule. 0 plus 0 plus 0 equals 0, and that's good because HCN is a neutral molecule. All right, so this is a good resonance structure. But now let's look at the lower example. This is hydrogen isocyanide. Now hydrogen is still 0, so that's not a big deal. 1 minus 1 minus 0. But the nitrogen in the middle now, nitrogen's group 5. That nitrogen has 4 bonds, 3 to carbon and 1 to hydrogen, 5 minus 4, and no lone pair electrons. So this formal charge, positive 1. The carbon on the end, group number 4, 4 minus 3 bonds to nitrogen, minus 2 lone pair electrons, 4 minus 3 minus 2, minus 1. All right. Now, if you add those 3 formal charges together, 0 plus 1 minus 1, they all go to 0. And that's good because hydrogen isocyanide is also neutral. But here's why chemists think that hydrogen cyanide, the top one, is more stable than hydrogen isocyanide, the bottom one. You have more positive ones and negative ones in this molecule than you do in the hydrogen cyanide. All of those are 0, and the bottom ones are negative. So the positive one, negative ones in the lower structure, those are like beacons, if you will. Positives will attract other negative things, and negatives will attract other positive things. So that nitrogen with a positive one in the middle will start attracting negative things like chlorides or oxides, stuff like that. And on the other hand, that negative carbon on the far right, that'll start attracting positive things to it. So HNC, the hydrogen isocyanide, will be more reactive. It has more positive and negative charges to it. Hydrogen cyanide at the top, everything is 0. It's like stealth mode, all right? Nothing positive or negative would see it, at least not readily. So this is the advantage of formal charges. Because there's more zeros, we would say hydrogen cyanide is more stable than hydrogen isocyanide. And it is. Hydrogen isocyanide, you have to keep really cold temperatures. You can't let it react with anything because it's very, very reactive. This is the advantage of formal charges. Here's carbon dioxide. Now, earlier I just showed it with 2 double bonds, and if you figure out all the formal charges, everything goes to 0. So oxygen on both the left and the right, because it's the same environment, 6 minus 1/2 of 4. This is 1/2 of the bonding pair electrons. I would usually just use 1 minus 2 to represent the number of bonds, but you can either count the bonding electrons or you can just count the number of bonds, either way. So I would say 6 minus 2 minus 4 gives you 0. The 4 on this side, those are the bonding, the lone pair electrons, and each oxygen has 4 lone pair electrons. But this number right here, I would just say the number of bonds. So 6 minus 2 bonds minus 4 gives you 0. You can also count the individual electrons. It's your call. Either way, both the oxygens are 0. And the carbon in the middle, 4 minus 4 bonds, or 1/2 of 8 if you're counting the electrons, no lone pair electrons, that carbon is also 0. All the formal charges together, the 0 plus 0 plus 0 equals 0, which is good because CO2 is neutral. The more zeros you have, the better. This is all zeros, so that means it's a good structure. It should be stable. And why we're doing this is because you can actually draw CO2 with a triple bond. Now, the carbon in the middle is the same electronic environment. All right, 4, group number 4 minus 4 bonds, it's going to be 0. But now the oxygen oxygens on the left and the right hand side are different. Oxygen with a single bond ends up with a formal charge of -1, and oxygen with a triple bond ends up with a formal charge of +1. So if you add those formal charges together, you still get 0. All right, carbon is 0, -1 for the right-hand oxygen plus +1 for the left-hand oxygen. You still go to 0, but it's not as good as the previous CO2 because you've got negative and positive ones. They're like little magnets that attract the opposite charge to them. So that positive oxygen will attract negative things to it. The negative oxygen will attract positive things to it. So people feel that CO2 with 2 double bonds is a better Lewis structure than if you have a triple and a single like you do here. This sheet sometimes people find helpful. These are ways to represent the best formal charges, and best in this case means formal charges of 0. So for example, if you have a boron with 3 bonds to fluorine or chlorine or whatever around it, that's going to give it a formal charge of 0. But you do sometimes see the structure on the left, which is a boron with 4 bonds. That gives it an octet, and that actually gives it a formal charge of -1 on the boron, so it's not as happy. All right. Carbon we're going to deal with a lot, and these representations here are all carbons with 0 formal charges. And you can notice that most of them are like 4 single bonds, or a triple and a single, or a double and 2 singles, etc., etc. I would ignore the carbon with a lone pair. That's a very rare kind of carbon. Carbon with a lone pair is called a carbene, and they're very reactive, but officially that would be a formal charge of 0. But you wouldn't usually see a carbon with a triple bond and a lone pair. That would give it a negative formal charge. Or you wouldn't see a triple bond carbon with nothing else on it. That would be a positive charge. So sometimes this is a handy thing to look at. We'll see the oxygen usually has a double bond or 2 single bonds to make it happy. The halogens are usually a single bond, etc., etc. This is just kind of a quick and dirty way to know your formal charges without calculating them. And again, the more zeros you have in your molecule, the better. So let's go back to boron trifluoride. Boron trifluoride, we listed it with 3 single bond fluorines. But in reality, we could have made a double bond to fluorine. All right, that would have given boron a double bond, and it would have been happy and have its octet. But oh wow, when you figure out the formal charges, fluorines with a single bond and 3 lone pairs are going to have a formal charge of 0. But if you start sharing electrons with fluorine, fluorine ends up with a +1, and then the boron, which is group 3, ends up with a -1 formal charge. So you start having weird formal charges when you start sharing electrons. That's why boron, aluminum, gallium, they're totally happy being just less than an octet. They have 0 formal charges. Fluorine, to the most of the time, like never makes double bonds. I don't know of any stable structure with a fluorine double bond. All right, fluorine is the electron king. It wants electrons more than anything else. So you really want to stay away from making double bonds to fluorine. Now, once in a while, if you're like in the lab with high temperatures or electric fields, you can do things with fluorine double bonds. But 99% of the time, and all stable structures, as far as I know, fluorine will never make a double bond. So here's a question you might see. It says, determine the formal charges on the formate ion. This is CO2H with a -1 charge. And I'd like you to figure out the formal charges on the oxygen on the left, the carbon in the middle, and the oxygen on the right. Well, if you look at the oxygen on the left, that oxygen has 2 lone pairs and 2 bonds, and it's group number 6. So formal charge for that one would be 6, which is oxygen. I would subtract the 2 bonds to oxygen, and you subtract each lone pair electron, so that's 4 total. It's going to have a formal charge of 0. Cool, stable. Carbon in the middle, group number 4, it has 2 bonds to oxygen, a single bond to hydrogen, and 1 bond to the other oxygen, 4 bonds total, and no lone pair electrons, so it's going to have a formal charge of 0. But the right-hand oxygen, still group number 6, it has one bond, but this has 2, 4, 6, 6 lone pair electrons. So this is going to have a formal charge of -1. So if you look at all those answers right there, it's going to be answer D. Now, the sum of the formal charges must equal the charge on the molecule or ion if there is one. And this thing has a -1 charge. So if you go 0 plus 0 plus -1, it equals the charge, which is -1 on the molecule, and that's good. So if you have a molecule with a charge, something is going to be non-zero, all right? And in this case, it's that oxygen with a single bond. And by the way, hydrogen is formal charge of 0, 1 group number, -1 bond, 0, okay? It's that oxygen, which is going to be the -1. So if you have an ionic compound, then something is going to be positive or negative. You can extend a Lewis structure theory by applying what's called VSEPR. VSEPR stands for valence shell electron pair repulsion theory. And it's a really cool way to figure out the geometry of the molecules you're looking at. And the punchline of all of this is that electrons want to be as far apart from each other as they can. So in the upper right-hand corner there's like those two kind of lobes looking things. Those represent pairs of electrons, all right? And they're both negative, and they want to be as far apart from each other as they can. So they're going to be 180 degrees apart, one totally opposite each other. In the middle of the lobes, that would be the central atom, all right? So that could be a carbon or a nitrogen or whatever. And if there are two pairs of electrons around it, they want to be as far apart from each other as they can. So the whole thing of VSEPR, electrons want to be as far apart from each other as they can.
According to VSEPR theory, the valence pairs surrounding an atom move to positions that minimize their repulsions.
If you have two lone pairs, they want to be as far apart from each other as they can. That would be 180 degrees. If you have three lone pairs, they want to be as far apart from each other as they can. That would be 120 degrees from each other. But if you have four pairs, then you do something else, which is a little strange. I'll show you some stuff here in a little bit. I do want to highlight this guide right here, which is called the Geometry and Polarity Guide. We're going to be talking about a lot of different names that are used to describe these geometries, and I've tried to compile all of them in this guide. So I do recommend that you get a printed version of this that you have next to you. You can answer these questions as we go through this here coming up. So if you have two pairs around a central atom, they want to be as far apart from each other as they can. And a great example of this is beryllium difluoride, BeF2. So the F atoms want to be as far apart from each other as they can. They're going to take up 180 degree positions. And this would be a linear relationship. The FBEF angle would be 180. That keeps the fluorines as far apart as possible. So in that rotating sphere right there, the middle of those two lobes, that would be the beryllium, and then the lobes represent the two fluorines, and they want to be as far apart from each other as they can. Sometimes, though, you have a central atom with three pieces around it, like boron trifluoride we looked at earlier. Boron trifluoride, those fluorines want to be as far apart from each other as they can, and they will be farthest apart if they are in what's called a trigonal planar geometry. So the fluorine-boron-fluorine angles are all about 120 degree angles. This is a flat molecule. So BF3 is actually flat, and we would describe the angles as 120 degrees. Now, when you add a fourth one, it might be tempting to say that, oh yeah, they would all be at 90 degree angles. So if you had a flat molecule with four pieces around it, it would be 90 degrees as the angle between them. But what really happens in three-dimensional geometry is instead of a 90 degree angle, you can get them a little further apart if you place them in what's called a tetrahedron. So notice that there's an example of a molecule, for example, CH4, and the carbon in the middle has 4 hydrogens around it. And instead of having them at 90 and 180 degrees, you can get more separation if you put them in a tetrahedron. So you can think about it like you have 1 on the top and 3 on the bottom. That's kind of a cheesy way to do it, but it works. But again, the advantage is you keep those lone pairs, those bonding pairs, farther from each other. Each of those CH bonds, again, is just a big thing of electrons, and you want to keep them as far apart from each other as you can because electrons don't like being close to other electrons. So 109 is better, farther separation than 90 degrees. That's why the tetrahedron dominates when you have 4 atoms around a central atom. If only they would have been able to keep it at 90 degrees, there's lots of things that we would have avoided as chemists, but alas, Mother Nature likes to keep them as far apart as possible. Tetrahedral wins over 90 degrees and 180 degrees. So let's go back to the ammonia structure we looked at earlier. And ammonia was a nitrogen with a lone pair and 3 bonding pairs. And let's describe this molecule now using VSEPR, okay? So what you would do is you'd want to count the total number of bonding pairs and lone pairs. And so around nitrogen, you have 3 bonding pairs to hydrogens and 1 lone pairs. So 4 pairs total means that that nitrogen is going to be in a tetrahedron, or it's going to be in a tetrahedral geometry. One of the positions will be that lone pair, which is on top, and the other 3 positions will be hydrogens. So chemists would describe the electron pair geometry, the EPG, as tetrahedral. The H and H angles are all about 109 degrees. Sometimes chemists like to talk about, though, what's called the molecular geometry, which is the geometry of what the molecule would actually look like if you could shrink yourself down to the level of the molecule. Now, lone pairs are just shimmering electrons. We saw in the last chapter how the electrons are actually just random kind of orientations. You wouldn't really see them or anything like that. So the molecule then would look like a 3-sided pyramid. Chemists would call the molecular geometry a trigonal pyramid. So if you have an electron pair geometry which is tetrahedral and one of the positions is a lone pair, then the molecular geometry is called trigonal pyramid because it looks like a 3-sided pyramid thing. Let's apply VSEPR rules now to the Lewis structure for water. Now, water is H2O. Notice that hydrogen is listed first. Hydrogen sometimes is listed first. We'll talk about this more later. It's listed first a lot of times for acids and things like that. For whatever reason, hydrogen is first. But anyway, when you draw the Lewis structure, you'll find that oxygen is in the middle. Hydrogen can't be in the middle. It always has to be on the outside. The oxygen has 2 lone pairs and 2 bonding pairs, so it has its octet. It's totally happy. But for us here now with VSEPR, what you want to do is first count the number of bonding pairs and lone pairs around your central atom. And oxygen has 2 lone pairs and 2 bonding pairs, 4 pairs total. So like with ammonia, that means that this is also going to be a tetrahedral electron pair geometry. In water, 2 of the 4 spots around the tetrahedron are taken up by lone pairs, and the other 2 spots are taken up by hydrogens. So if you think about then the molecular geometry, which is what that thing looks like, knowing that the lone pairs would be invisible but still present, you're going to end up with an HOH angle, which is bent. It's going to be about 109, which is what at the time you see most of the time with tetrahedron. So for water's geometry, then, we would describe the EPG, electron pair geometry, as tetrahedral, and the molecular geometry as bent. That's about 109 degree angles right there. So let's apply VSEPR rules to sulfur dichloride, SCl2. What would be the molecular geometry of SCl2 specifically? So when you draw the Lewis structure for SCl2, the sulfur's in the middle of the chlorines. The sulfur has 2 lone pairs and 2 bonding pairs around it. So if you count up the total pairs, that's 2 bonding plus 2 lone pairs, 4 pairs total. That's going to be tetrahedral. But tetrahedral is the electron pair geometry around the sulfur. So we know that all of those angles will be about 109 degrees or so. So to figure out the molecular geometry, we look at just the bonding pairs. There's 2 of them. And in a tetrahedron, the bonding angles are always about 109. So believe it or not, SCl2 has the same molecular geometry as water. The ClS-Cl angle would be bent. It would be about 109 degrees because it's in a tetrahedron. It'll look just like water, except you'd have sulfur in the middle and chlorines on the outside instead of oxygen in the middle and the hydrogens on the outside. So kind of cool. Methanol is CH3OH. Methanol is an example of an alcohol. Alcohol in the chemistry world is a family of chemicals that have an OH on them, and we'll talk more about that in a future lecture. But if you draw the Lewis structure for methanol, that CH3 has a carbon with a tetrahedral environment. So tetrahedron means 4 bonds. 3 of the bonds are to hydrogen, and 1 of the bonds is to oxygen. Then the oxygen itself has a bond pair to hydrogen and 2 lone pairs on it. So that would be the Lewis electron dot structure for methanol. Now you can go farther though, because anything that's tetrahedron should be about 109 degrees. So if someone asked you what the HCH angle was, angle 1, or the HOC angle is, angle number 2, well, both of those are tetrahedral geometries. And so both of those would be about 109 degrees. And that's kind of a cool thing to know. So you can actually make predictions. Now, a Lewis structure is not written with any kind of bond information at all. So notice in both of those Lewis structures, the HCOH, that's like flat, 180 degrees, right? And the H's are above and below there in that CH3 group. But in reality, you can interpret that using VSEPR to know what the actual angles are. And anything that's tetrahedral would be about 109. Anything that's trigonal planar would be 120. Anything that's linear, 180, blah, blah, blah. So a Lewis structure is great for scientists who can't draw, and I put myself in that list, by the way. You don't have to include any angle information. You don't have to show things and stuff, which is really cool. However, the hip chemist, which is what you should also consider yourself to be, can use VSEPR to interpret the geometry. So that little animation there shows a better representation of what methanol is. And you can see there's kind of cool angles, all about 109 degrees. It doesn't look anything like the Lewis structure, but the Lewis structure can be interpreted to figure out what the molecule looks like. So that's kind of a cool thing about VSEPR. It allows you then to visualize, at least in your mind, what the molecule would look like in the real world. Acetonitrile is a methyl group with a cyanide on it, and when you draw the Lewis structure out, it also has one of those CH3 groups like methanol did, but now it has a carbon-nitrogen triple bond. And the question is, what are bond angles 1 and 2? So bond angle 1 would be the HCH, but bond angle 2 would be the CCN angle. So bond angle 1, HCH, that carbon central atom is tetrahedral. There are 4 bonds around the central carbon right there. And again, anything with 4 bonds will be tetrahedral, and that means 109. But the carbon in angle 2 is kind of cool to talk about because it has a triple bond on one side and a single bond on the other. Well, we're going to see in the next chapter that double bonds and triple bonds are basically like one big cloud. They kind of stack on top of each other. So we saw earlier how if there's only 2 bonds, the bonds want to be as far apart from each other, 180 degrees. Well, triple bonds, double bonds, and single bonds count as just one big cloud, one big bond. So that carbon number 2 in bond angle 2 has essentially like 2 bonds around it. That's going to be 180 degrees. So triple bonds, double bonds, single bonds, they all count as like a big bond, if you will. So that central carbon in angle 2 has a triple bond on one side, a single bond on the other. That's like 2 clouds of electrons that want to be as far apart from each other as they can, 180 degrees. Boron trifluoride, things that go under the octet, can also apply these rules just as well. The boron in the middle and the Lewis structure on the right has 3 fluorines. They each want to be as far apart from each other as they can. That's a trigonal planar electron pair geometry, and those angles are all about 120. So again, note that the Lewis structure for BF3 looks like it's kind of 180 and 90 degrees, and that really is nowhere near what the actual molecule looks like, which is right there. It's more like 120 degrees from each other. So again, Lewis structures don't have to have any information about the actual geometry, but you can interpret a Lewis structure to give what the molecule would actually look like. And if you had drawing skills, which I don't, you could probably draw something at 120 degrees. It's kind of a cool extension, and artists will have a wonderful work of this compared to my poor artist skills. Now, you can go past the octet too, and this is another important consideration. So here's an example of phosphorus pentafluoride, PF5. And phosphorus in that middle there has 5 fluorines around it. So this is going now beyond the octet, and there are absolutely rules to figure that out. So if you have 5 clouds of electrons around a central atom, they refer to that as a trigonal bipyramid, all right? And a trigonal bipyramid just has 5 electron pairs, if you will, around the central atom. Now, what's really interesting is that when you have a trigonal bipyramid, there's several angles to pay attention to. There's like a middle part, and that's like a trigonal planar geometry we saw earlier, like with BF3. All of those angles are 120 degrees. But then you have a fluorine on the top and a fluorine on the bottom. And if you compare the top or the bottom fluorines to one of the plain ones, those are 90 degrees. But in reality, there's a third angle too, because the F angle that goes right up and down the middle, that's 180 degrees. So these are kind of wild. All right, you've got 3 angles to think about, 90 degrees, 120, and 180, and that'll be important for some stuff we're going to talk about here in a little bit. If you have 6 pairs around a central atom, which is also possible in period 3 and lower, then you get to an octahedron. An octahedron is actually somewhat common. An octahedron has everything at 90 degrees and 180 degrees. So you can see that most of the angles that are listed are 90, but there's also 180 degrees when you go from like the top to the bottom, if you will. So think about 90 and 180 degrees when you think about it. Again, all of these rules are just the electrons trying to stay as far apart from each other as possible. And I'd also like to re-highlight this geometry and polarity guide. It'll have all of these names, the bond angles, even the polarity and stuff listed. I tried to make it a pretty cool guide for you to start learning this stuff and figuring out what's happening. Let's go back to our sulfur tetrafluoride example we saw earlier, where sulfur was going beyond the octet. And that sulfur had 4 fluorines and a lone pair around it. That's what made it go past the octet. Well, if we wanted to figure out the geometry then of it, it would have 5 pairs, and 5 pairs makes it a trigonal bipyramid. So trigonal bipyramid is when you have something above and below a trigonal planar plane. We'll think about 90 and 120 angles like it shows there, as well as the 180 degrees. Now, it is important where the lone pair goes here, because as we talked about, or I mentioned earlier, unshared pairs are bigger than bonding pairs or shared pairs. And so you want to give the lone pair or pairs as much space as possible. And you have a better molecule when you put that lone pair in one of the middle parts right there. In one of the parts that's the trigonal planar, if you will, part. And why that is you want to have as few 90-degree angles with the other atoms as possible. So if you put one there in the middle part, there are 2 90-degree angles, one for the fluorine above and one for the fluorine below. And that's actually better than if you put a lone pair on the top, like if you replace that fluorine with the lone pair. Then then you'd have 90-degree angles for 3 different fluorines, and it's better to have just 2. So long story short, if you have a trigonal bipyramid structure with 1 lone pair, it always creates what's called a seesaw. And this picture in the upper right shows what it would look like, knowing that the lone pair, which would be right here, by the way, in the structure, knowing that the lone pair is invisible. A seesaw, if you put it 90 degrees, would have like a kid on the left and the right, the top and the bottom, if you will, fluorines that could go up and down. If you use your imagination, you can see it. If you don't worry about it. But again, that geometry and polarity guide will help you with all this kind of stuff. So 1 lone pair goes on the equator, if you will. It's going to have then a better structure than if you put it on the top. These are the different orientations you can have for both trigonal bipyramid on the top and octahedral on the bottom. So first of all, note the first one on the left-hand side. This is a trigonal bipyramid without any lone pairs, like PF5. Then you have EPG and MG the same. So for PF5, which has no lone pairs, electron pair geometry would be trigonal bipyramid, and molecular geometry would be trigonal bipyramid. It's the same name for EPG and MG if there are no lone pairs. However, if you have 1 lone pair, then it's better to put it kind of in the plane, as we talked about in the last part. This creates a molecular geometry of seesaw. So for SF4, we would say the electron pair geometry is still trigonal bipyramid, but now the molecular geometry is seesaw. If you keep going, the T-shaped, it would be the molecular geometry with 2 lone pairs. And if you have 3 lone pairs, they all go in that central plane. That actually creates a linear molecular geometry. Now again, all 4 of those, the EPG would be trigonal bipyramid, but you do change the molecular geometry name as you add and subtract lone pair electrons. The bottom is for octahedral electron pair geometries. So all 3 of those would be octahedral EPG, no lone pairs, EPG and MG the same. If you have 1 lone pair, it creates the square pyramid. And if you have 2 lone pairs, it creates what's called square planar. So at this point, I need to point out, it's really important, if you've been in other classes, sometimes they'll say like trigonal planar, you can get by with just saying planar. And you can't do that here in Chem 221 because square planar and trigonal planar both have planar in them. So you have to say at least like trig plane or something like that. So I know it's trigonal planar, and square plane, so I know it's square planar. And pyramidal is even worse. You can't say just pyramidal. You have to say trigonal pyramid, square pyramid, stuff like that. Trigonal bipyramid, lots of different pyramid names. So just realize we're kind of in the big kids class. You got to use big kids terms. Don't just use pyramid, planar, stuff like that. It doesn't fly very well in this class. So this next topic we're going to talk about is molecular polarity. And it's a pretty important topic, as I'll show you here. So for example, let's compare water, H2O, and methane, CH4. And both of these have very similar molar masses. So for water, if you add up 2 H's and an O on the periodic table, you get 18.02 grams per mole. If you add up a carbon and 4 hydrogens on the periodic table, 16.05 grams per mole. So almost the same number. They have similar geometries. Electron pair geometry is tetrahedral in both, although water is bent molecular geometry. CH4 that doesn't have any lone pairs would also have tetrahedral molecular geometries. But goodness, look at the difference in boiling points. The boiling point for water, if you tried to boil water on a stove, 100 Celsius, 212 Fahrenheit, all right? Methane, which is natural gas, by the way, more or less, minus 161 Celsius. So why would something in a similar electronic environment with about the same mass have such different boiling points? I mean, it's just crazy. The difference between those is like 260 degrees. It's just a crazy, crazy difference. And another thing, why is water so good about dissolving ionic compounds? Like if you put sodium chloride in water, the sodium chloride goes away. It becomes sodium ions and chloride ions. Why is water so good about dissolving these ionic compounds? And both of these answers come from what's called molecular polarity, which is a really important consideration in chemistry. And it affects things not only a lot in Chem 221 through Chem 223, but all the way through biochemistry and beyond.
When the balloon is rubbed with wool, the wool imparts a static electric charge to the balloon. When we place the balloon near the water, the stream is attracted to the balloon. The polar water molecules act as though they have an electric charge as well. Water molecules carry no overall electric charge, but they do exhibit polarity. The positively charged end of the water molecules and the negatively charged balloon attract each other.
This is kind of a fun thing to do if you have small kids. You can rub a balloon with a piece of fur and it creates a little bit of a charge. And if you have a very, very thin stream of water going down, you can actually bend the water to the balloon, which is kind of a cool thing. And this is a fantastic phenomenon that's only possible because water is very polar. And if you look on the right-hand side there with a little animation, you can see how the HOH is kind of like a V. Now we know that the HOH is kind of a V because water is in a tetrahedral electron pair geometry environment, and the HOH angle is bent, but the tetrahedron makes the HOH angle about 109 degrees. Water has, as we saw earlier, two lone pairs on it. So those lone pairs are centers of negative energy, and negative energy will attract to positive things and repulse other negative things. On the other hand, the two hydrogens here, they're going to be slightly positive. They're going to attract negative things and be repulsed by positive things. So on this right-hand animation, you can see how all the water molecules, they kind of orient themselves so the H's are closest to the negative balloon. And the oxygens are getting as far away as they can from the balloon because that's where the negative side is. So the molecule of water itself is polar. The molecule has a slightly negative side, which is the oxygen, and it has a slight positive side, which is the hydrogens. And this is an example of molecular polarity. It's not just a bond polarity, like OH would be a polar bond. The whole molecule has a slightly positive and a slightly negative side. And this is an important consideration when it comes to reactivity. So a molecule will be polar if you have polar bonds, i.e. they're made of different things, and you have to have an asymmetric or a molecule which is not symmetric orientation. So let's look at some examples. All of these examples have a symmetric orientation of atoms around the central atom. And what that means is that everything is the same. So on the first one, this would be an example of like beryllium difluoride. The beryllium would be the gray in the middle, and the fluorines would be on the outside. So around the beryllium, you have nothing but fluorines. That would be a symmetric environment, all right? There's no lone pairs. Everything is the same fluorine around it. Good to go. Boron trifluoride, BF3, would be another example. Everything around that boron is the same, all fluorines. Like you don't have two fluorines and a chlorine, or a hydrogen and two iodines. Everything is fluorine, so that would be symmetric. This is an example of a tetrahedral symmetric molecule, CF4. Everything around the carbon would be the same. You could also have CH4 or C-bromine 4. I mean, anything where the molecule is surrounded by the same kind of things, that's cool. And lone pairs count here, so no lone pairs, blah, blah, blah. PF5 would be 5 fluorines around the central atom for trigonal bipyramid. Sulfur hexafluoride, SF6, would be an example of an octahedral that was symmetric. So if you have a symmetric molecule, that molecule will be non-polar. It doesn't have the polarity we're going to talk about. But you can probably imagine that there's a lot of examples where things will be polar. Like you'll have, for example, in SF6, one of the F's will be replaced by a chlorine, or it'll be replaced by an oxygen or whatever. It breaks the symmetry. That makes the molecule polar. So if you have to guess, I tell people sometimes guess polar because there's a lot more of them that are polar than non-polar. However, it's better to kind of think about it and stuff. And we'll go through some examples here of how this works. So let's compare carbon dioxide and water. Which one of these is polar? And the best thing to do, draw the Lewis structures. So carbon dioxide is a carbon in the middle of two oxygens with double bonds. I'm not showing the lone pairs here, but they would be two lone pairs on each oxygen. Water, on the other hand, as we've seen, has a bent molecular geometry and two lone pairs on it. So around the carbon in CO2, we have just double bond oxygens. That's a symmetric molecule. So the molecule is nonpolar. Now, each carbon-oxygen bond is polar. Oxygen pulls a lot more. It has a bigger electronegativity than carbon. However, the pull to the right is canceled by the pull to the left, if you will. So the overall molecule is nonpolar. So you can have polar bonds, but a nonpolar molecule. But you don't see that with water because those angles are 109 and the angles don't cancel out. Like with CO2, it was 180. With water, you have 109-degree angles. So the oxygen-hydrogen bonds, each of which are polar, they don't cancel. If you've done anything with vectors in math, each of those OH bonds is like a vector, like a dipole, and you can add the vectors together to see if they cancel. And with 109-degree angles, they don't cancel. Now, if you don't know what a vector is, don't lose any sleep about it. You don't need to know about that, but that's really what's happening here. If the important thing here is that everything around that water is not the same because you've got two lone pairs, and lone pairs are different than hydrogens, so everything around the oxygen is different. This is going to be a polar molecule. Now, this is the measurement of the polarity, 1.85 dBi. That's what the capital D stands for. You don't need to worry about that. You can actually measure the polarity around water. It's pretty strong. CO2 would not have a dipole moment. There's nothing to measure. It would have a 0 dBi measurement, if that's where you want to talk about. All three of these molecules have a central atom and three atoms around the central atom, or AB3. So BF3, Cl2, CO, and NH3. So in boron trifluoride, boron would be the A, the central atom, and the three fluorines would be the three Bs. In Cl2CO, the carbon is central, and it has two chlorines and an oxygen around it. And with nitrogen and with ammonia on the far right, nitrogen would be the central atom A, and each B atom would be one of the hydrogens. So again, if you want to see if they're polar or nonpolar, do a Lewis structure. So boron trifluoride has boron with just fluorines around it. Each boron fluorine is very, very polar as a bond, but because everything is the same, it all cancels out. BF3 is nonpolar. And again, you don't need vectors to figure that out. You just need to see that that boron has nothing but fluorines around it. No hydrogens, no lone pairs, no oxygens, whatever. Just fluorines. That makes it a symmetric environment, symmetric things, nonpolar. Now, Cl2CO, though, does not have a symmetric environment. It has a carbon-oxygen double bond and two carbon-chlorine bonds. So that molecule doesn't have anything the same. C double bond O will have a different polarity than CCl will, so nothing's going to cancel. That's a polar molecule. And ammonia, NH3, at first looks like it might be symmetric until you draw this Lewis structure. There's a lone pair on that nitrogen, and lone pairs are enough to break the symmetry. So around that nitrogen in NH3, you have three hydrogens and a lone pair. That also is not symmetric. Lone pairs break the symmetry too. That's going to be a polar molecule. So again, more often than not, guessing polar is probably okay. But again, be careful because some things like BF3 will be nonpolar. So here's the kind of question you might see. It says, which of the following molecules is polar? All right. And maybe none of them are polar. It's hard to say. But anyway, the best answer here would be to draw out a Lewis structure for all three of them. So for example, boron in boron trichloride, that's a trigonal planar. Carbon and carbon dioxide, that's a linear electron pair geometry. Nitrogen N2 would be two nitrogen atoms together, and ClF would be a chlorine connected to the fluorine. However, even without drawing the Lewis structures, Cl and F, those are two different atoms, and they're connected to each other. Fluorine is the most electronegative, like we said. Chlorine is less, so there's going to definitely be a polar molecule there because fluorine pulls differently than Cl. Now, if there's two nitrogens like N2, they will cancel each other out because nitrogen pulls, but they pull equal and opposite. That's going to be nonpolar. And we've seen how carbon dioxide is nonpolar. Two double bond oxygens at 180 degrees, they cancel out. And boron trichloride, that boron has nothing but chlorine around it. That's going to be a nonpolar molecule as well. This picture shows CH4 methane being replaced by one chlorine at a time until you get to the far right, which is carbon tetrachloride, CCl4. And notice what happens to the polarity. So on the far left-hand side, CH4, everything, all the carbon is completely surrounded by hydrogens. So everything around the carbon is the same. This one's going to be nonpolar, all right? And on the far right, even though chlorine is pretty electronegative and it pulls electrons pretty strong, everything around the carbon is the same, all chlorines. It's also nonpolar. But if you start now back on the left again, CH4, you replace one of the carbons with a chlorine. Hey, now we've got an asymmetric orientation of atoms. That carbon has 3 hydrogens and 1 chlorine. Everything is not the same. Polar. If you have a dipole moment, that means it's polar. If you replace a second hydrogen with a chlorine, still asymmetric, polar. Replace a third hydrogen with a chlorine, now again asymmetric because 1 hydrogen and 3 chlorines, nothing's the same, polar. But again, you had every position with hydrogen you replace with a chlorine, that's going to have a symmetric environment once again, nonpolar. So the far extremes are nonpolar, but everything in the middle is polar. It shows the importance of knowing if something is symmetric or asymmetric. All of these molecules shown are actually symmetric, and it's something we'll talk about more in future lectures. But if you have like a central point where everything is the same around it, it's going to be nonpolar. So as an example, this compound ethene in the upper left, you can have like a dot right there in the middle, and everything on the left and the right is the same, and this is a flat molecule. That's going to be nonpolar. And acetylene, which has a triple bond, you can do the same thing. Everything to the left and the right of that molecule will be the same, nonpolar. Now with this molecule, you have to be a little bit more creative, but if you put a dot in the exact middle, everything around that dot is the same, like a CH at all different places, so that's what makes it nonpolar, etc., etc. So there's a lot of nonpolar molecules out there, but again, there's a lot more polar molecules too, so usually if you just guess polar, you'll be okay. But again, try to think about it in terms of symmetry if you can. Okay, so that's it for the Chapter 4 complete lecture. I really appreciate you being here with me and learning this material, and I sure hope it's been helpful. If you have any questions on anything, definitely reach out to me. There are certainly more resources out there for you to learn the material should you need it. Again, good luck with your studying. Have a great day.